So 7.4 is on the addition and subtraction of radical expressions, ones with like square roots or cube roots, etc. Radicals are similar if they have the same index, meaning they're both square roots, or they're both cube roots, or they're both fourth roots, and they have to have the same radicand. And the radicand is that part underneath the square root. So they're only similar if they're both like square root of 7 or square root of 12, or they're both cube root of 9, or whatever it might be. So if they are similar, then we're going to be able to add or subtract them. That's why we need to know what is meant by similar. So 3 root 7 and 5 root 7, are they similar? It doesn't matter about the coefficients, it matters about the index being the same and the radicand, the part underneath the square root, being the same. So these are. So yes, they have the same index, being square root, so index of 2, and same radicand, which is in this case the 7. So they're both square roots and they're both a radicand of 7. This next one, they're both cube roots and they both have a radicand of 5. So yes, same index, it's a 3, and same radicand, in this case 5. Number 3, root 15 and cube root of 15, are they similar? Well, one thing you want to do when you're checking is make sure your roots are as simplified as possible. 7, 5, 15 have no square or cube. They don't have an nth root. It can't be simplified any further than they are, so it's easy to determine. They have different index, and although they have the same radicand, they do have different index. So it needed to meet both criteria. This is no, and it's because they have different indices or index values. So a 2 versus 3. Number 4, are those similar? So they're similar in the sense they're both square roots, but they're not actually considered similar radicals because the radicands are different. So it's like, you know, if I was, you know, square root of 5 and square root of 2, I cannot combine them into another square root of so many square roots of 5 or so many square roots of 2, because they're just not both square roots of 5 or both square roots of 2. So when they are similar, you can then add or subtract them based off of the coefficients. Like if you had 5a plus 3a, you would have 8a. It's a similar idea. So here we have 5 root 3 minus 1 root 3. Same index, same radicand. So I can take 5 of these root 3's and subtract 1 of the root 3's. So I'll have 4 of the root 3's. So again, it's just the coefficients. 5 minus 1 is 4 of my root 3's. So I have 3 root 2's, right, 3 square root of 2's here, and I have 8 square root of 2's there. So I can combine that to 11 square root of 2's. And then I have negative 2 root 3, and I have positive 7 root 3. So I will end up with 5 root 3's. That's as simplified as this can go because those are not like terms, so, or like radicals, so they're not able to be added or subtracted. Root 18, I mentioned just a moment ago how you want to have your roots simplified so you can see if there is the same radicand part. So root 18 is the same thing as thinking of, well, let's just do 9 times 2. I have square roots. I'm looking for 2 of something. I have 2 3s, so I can pull out a 3. And then my leftover would be 2. And then 50, you might think of as 5 and 10, or you might think of 25 and 2. No matter what you end up doing, you have a group of 2 5s. I'm doing groups of 2 because it's square root, and I have this leftover 2. Square root, leftover 2. So now it's a little more obvious that although it doesn't look like they have the ability to be added because they have different radicands, once you've simplified it, you actually can, and it would end up being 8 root 2s. And again, you cannot add the contents underneath the radicands and put it under one root because it only works for factors, not a product. Sorry, not sum or difference to combine. This next one, in order to add fractions, you need a common denominator. So you might think of that at first and think, oh, I need to do 2 over 2 to get the denominators both be 6. And that is one method. So I can just multiply by 2. But I can't quite add that yet, other than to say like this. But I can think about root 12 as 4 times 3, so that's 2 root 3. So I have 2 root 3 plus 2 root 3 over 6. That's 4, 2 of them plus another 2 of them. You're going to have 4 of the root 3s, 5 by 6. The coefficients, this is 4 times, so I can just simplify the 4/6 part by dividing both by 2. So that's one option, and you don't have a root in the bottom, you don't have a fraction under a root, so that is considered simplified because the 3 is as far as it can go there. The other option would have been to recognize that you can simplify the root 12 to 2 root 3. Then you can also simplify that fraction, and now you have a common denominator of 3. So you have root 3 plus 1 root 3, that's 2 root 3s over your common denominator. So you could have approached it either way. You could also have approached this with making this 6 and simplifying this way back here. So there's a couple different options. Just make sure you don't combine unlike things and that you do think about how you can reduce your radicand. The next example, again, it doesn't look like the radicands are the same, but we actually can add these because you can represent it in such a way where you do have the same radicand. This 24 is 2 and then cube root of 3. And then for the a's, you have exponent 5 divided by 3, so it goes in 1 time with 2 left over. There's already a b out here, and then which I could have put earlier, I just didn't. And then this b, and there's 1, it doesn't go into 3, so it's b there. So that's that one. And then plus, we have the 3, we have the a already here. Then the cube root of 81 is exactly, no, sorry, we're doing cube root. Cube root of 81, it's 9 times 9. So we'd have 3 come out, and this leftover 3 underneath, and again of a cube root. So there's the 3 root 3 from the 81. This 3 is from this 3. This a is from this a. This a squared, 2 does not go into 3, so they're left over here. B, we can pull out one group of 3. That's pulling out 3 of them. We need 1 more. So now, when I look at this, I do have common radicals because my radicands are the same, the index are the same. I have 2ab plus, this becomes 9ab. So 2ab plus 9ab is 11ab of my cube root of 3a squared b. Now, if these were not like terms themselves, then I would have had to say, like, for example, if this said 2ab and then this said 5c, then it would be 2ab plus 5c, that quantity times the common radicand. In other words, you could factor out this common root, this common radical. And just be careful that it looks like an index and not the exponent of your b. That's one common thing that is a little bit tricky. Sometimes students make it look more like an exponent here and not an index, so just be clear. And then number 10, both of these terms are being divided by 2, so 2 divided by 2 is 1, and for root 5 divided by 2 is 2 root 5. So again, 1 plus 2 root 5. Don't worry about the radicand. It's about the coefficient. I have 4 of these. I'm dividing by 2, so I'll have 2 of those, and of those is the root 5. Alternatively, you can do it kind of like we were doing in the last chapter, where you factor to see if you can simplify a fraction. I can factor out a 2, and then these 2's would reduce. And so you'd end up with 1 plus 2 root 5. And that is it for 7.4. The main part of this being that it's just about the coefficients. You add them, but you keep the same like radical portion, or you can divide, but you keep the same like radical. So you don't divide the root part, only the whole factor, and you use its coefficient to do so. I hope that helps with 7.4.